So thank you for coming back. So let me say a few words about what we have already done so that you remember. So we have had period matrices tau, which were now in the Ziegler-Lapa half space. So these were G by G symmetric matrices, complex coefficients, which had a positive definite imaginary part. And given such a setup, and given a complex vector, a G-dimensional vector, I was able, one can define the theta function, right? Which was the unique section on the abelian variety of the corresponding bundle, right? So on the abelian variety A sub tau, e to the G, e to the G tau, and maybe I wrote tau on a different side, doesn't matter. I mean, it does, but not here. There is a unique section, okay, up to scaling. So the only sections of the corresponding line bundle on the abelian variety is the theta itself, which is to say the only holomorphic function on C to the G with the automorphic property of this guy with respect to adding elements like that is the theta function itself or a constant multiple of it. This is what we had. And then we had a statement that if I were to compute the dimension of the space of sections of n's powers, so this was going to be n to the g. Okay? And from that, we got a very important formula, which I want to remind you of, which in its simplest form says that if I take the square of the theta function, I can express it as a sum over 2 to the g elements, which are a basis of this space for the second power, which are objects of kind, where I have defined this as basically the theta function of the argument 2 tau and 2z with some shift in z. Okay? This is so-called Riemann's bilinear addition theorem. Okay? So well, maybe I should write. This is some exponential factor that I'm ignoring for the expository purposes, and it's very simple, times the theta function of 2 tau 2z. And this came basically for free. This also demonstrates the relation between theta functions as functions of z and theta functions as functions of tau. Notice there is somehow tau 0 here. There is a more general version, which is called the isogeny theorem, which generalizes this in two ways. First, instead of z and z, I have theta of tau x times theta of tau y. And then here I'll get x plus y over 2, and here I'll get x minus y over 2. That's the easy generalization, that's an exercise. The harder generalization is to say that for any finite map of abelian varieties, we have one abelian variety map into another abelian variety by a finite surjective map, which is linear. That's called an isogeny of abelian varieties. Something like that works. That is a true statement. I won't be able to write the formula. But this is a general setup. Yeah. Thank you. That was just a typo. No hidden meaning. And then, in particular, when we started the first time here, I talked about genus 1. And then there is a theta function, which we all know and like. Maybe they're called theta 1, 2, 3, 4. I don't use that language here. But we discussed that theta 1, which is the odd one, has a unique 0 at 0. The usual theta function, which is the one I wrote, has a 0 at the center of the parallelogram. And as a result, I told you that you can write any function on an elliptic curve on a genus 1 Riemann surface as a rational expression in theta functions, right? Last lecture was devoted to this and more, which was generalization of this to higher dimensional abelian varieties. What I'd like to devote today's lecture to is higher genus Riemann surfaces. And the first half of the lecture, or the first part of the lecture, will be trying to build a theory like that, and then I'll try to contrast higher genus Riemann surfaces with higher dimensional abelian varieties. Okay, that's the plan. So you all know what the genus G Riemann surface is. I won't tell you what that is, but the question I'd like to address is how to write down any meromorphic function f C to P1. So again, by a meromorphic function, I mean a holomorphic map from C to P1 on any Riemann surface. So this is a direct generalization of what we did for genus 1, where somehow our life was very easy. We had a theta function, which was not really a function, but it had a zero at just one point on the Riemann surface. Okay? You can convince yourself that's not going to work so nicely for higher genus. Right? G is equal to 1, which is why the theta function had a unique 0. Not going to work in higher genus. There is a theory that generalizes that. That's my goal. Okay? With that prelude, we'll have now an interlude. Are we ready for some pain and suffering? No. But we'll go there anyway. So I have to remind you of the language of line bundles on a Riemann surface. Okay? I think this is a much less painful version of the first time. So I want to talk about divisors on a Riemann surface. Definition: a divisor is a sum over all points in P in C of AP times P. It's just a formal linear combination where the number of P, such as the coefficient is non-zero, is finite. Okay? So it's a finite linear combination of points. I'm being sloppy as to what AP are. For me today, they're integers. Algebraic geometers prefer rational numbers in many situations, but these are numbers. Then divisors on C are the set of all divisors are an abelian group, because I can just formally add any two such things, right? A divisor, usually denoted D, has a degree. The degree of the divisor is just the sum of all the coefficients AP. Finite sum, so it's a number, so it's an integer. Okay? And I'll write div D for degree D divisors. So far, all very innocuous, right? Just complete formality. Why is that useful? Is because you can define for any meromorphic function f C to P1, what is the divisor of f? The divisor of f is by definition just the sum of all points in P and C of the order of f at the point P times P. Okay? What is this order? It's a vanishing or pole order. So if it's vanishing, then it's a positive integer, which is a positive order of vanishing. If it's a negative number, that's a pole, right? So a second order pole will show up with a coefficient minus 2. A fourth order 0 will show up with coefficient plus 4. A function, a meromorphic function on a compact Riemann surface has a finite collection of poles and a finite collection of zeros. So it's a divisor, meaning the sum is finite. All good? Raise your hand if this is second or maybe first nature to you. Don't be shy. Okay. So there are some people, but this is so far innocuous. Observation. The degree of such a divisor is 0. The number of poles of a meromorphic function is equal to the number of zeros of a meromorphic function counted with multiplicity. Proof. One-line proof. Integrating is fun. This is more general than integrating. This is also holds over finite fields. Computing integrals of forms of a finite field is a very interesting subject. You've heard some things about that. But this is just a look at this as a map from C to P1. The zeros are the preimages of 0. The poles are the preimages of P1. This is a finite map. It has a degree. So the number of preimages of 0 is equal to the number of preimages of infinity counted with multiplicity. Okay, I've proven this. Okay? This argument is an algebraic argument. I really never used the fact that we're over complex numbers. You may not care. Okay, but that's a statement. Okay, now recall a notion of line bundles. Line bundles. Okay. Line bundle in the Riemann surface, right? So this means I have local charts on each chart. This is just the product of the chart times C. And there are transition functions which are telling me how to glue on the overlap of charts, and they are linear in the fiber direction, okay? So if S is a section then I can try to define the divisor of S. This is going to be defined by exactly the same formula, the sum of, bless you, P and C of the order of S at the point P times P. And I claim this is well defined. So what's a section of a line bundle? You know, at each point, you choose a point on the fiber, right? Locally, this is a holomorphic section at this point, right? So locally, in a chart, it's just given by a holomorphic function. I know what the order of 0 of a holomorphic function is, no problem. The problem is I don't have global coordinates, so I may have to switch to a different coordinate. But the coordinate change is just multiplying by an element on C star. It doesn't vanish. The change of coordinates cannot vanish. It's a map to C star. So it doesn't change the vanishing order, right? If you have a function z squared and now your z has suddenly become 2 times w, the order of 0 did not change, okay? This also works for meromorphic sections, where I allow poles. Okay? Same argument, right? So again, I have what is a line bundle? I glue it from local charts. In each local chart, S is just a meromorphic function. So I choose this chart, I compute its pole order in some chart around P. But then I have to convince that it's independent on which chart I work in. But if I go to a different chart, the coordinate on the fiber just got multiplied by some nowhere 0, nowhere infinity transition function. So that doesn't change vanishing orders. Okay? Notice that I'm no longer claiming that the divisor of any section, meromorphic section of any line bundle is 0. Whatever I was saying here does not apply. And this is definitely not true. Okay? So given L and given S, which is a meromorphic section of L, I really don't like this notation, so I'll try not to use it, okay? I don't like writing meromorphic sections, not nice. Algebraic geometers are good with holomorphic stuff, meromorphic is too hard. Okay, so any other section S1 of L is equal to S times F, where F is any other meromorphic section, where F is a meromorphic function, right? Because if I take the ratio of S1 and S, this no longer transforms in any way. If I change coordinates, S1 transforms, S transforms the same way. The transformation cancels out. Okay? Moreover, what you can observe is you can compute the divisor of S times F. What is this? You go over all the points P and C and you compute the vanishing order of a product of two things. Locally, this is just a function. So the order of vanishing of a product of two functions is the sum of their vanishing orders, right? So the divisor of S times F is the divisor of S plus the divisor of F. right? More generally, doesn't matter that f was a function, f could have been a section of some other line bundle for all I care. Okay? So what this tells you is that for any two meromorphic sections of a line bundle, their divisors differ by a divisor of a meromorphic function. Okay? Definition. Principal divisors P div of C is the group of divisors of all meromorphic, this is a subgroup of all divisors in C, of all meromorphic functions on C. Why is it a group? Well, because if I have divisors of two functions f1 and f2, the sum is the divisor of f1 times f2, so it's a group. So it's closed under the obvious addition method. Okay? Definition. The Jacobian of degree d of C is the Jacobian in degree d of C is the group of divisors of degree d, so this is degree d divisors, quotient by principal divisors. So notice all principal divisors are divisors of meromorphic functions. They have degree 0. So if I take a degree d divisor and add to it a divisor of degree 0, the degrees add up. The degree defines a morphism from the group of divisors to Z. Okay, formal way to say this. So this acts here, and I can take a quotient. Okay, so that's the quotient of this space by this. The group of principal divisors is a subgroup of the group of all divisors. It's not a subgroup of this, but I can take a quotient by adding an element here. Okay? That is the definition of a Jacobian of a curve. Why would you care about it? Well, for many reasons. Well, first of all, it is the Jacobian that you know, except I feel very bad saying the word the, because there is a d here, which I fixed, right? And we have to agree what d you want. And as the end of the coming to an end interlude, I'll spend 2 minutes complaining that you have to be careful, okay? So why would you care about this? Because this somehow measures all divisors, degree d, up to meromorphic functions, right? So in particular, so if S1 and S2 are meromorphic sections of the same line bundle L, then the divisor of S1 is equivalent to the divisor of S2 in the Jacobian. Okay? Because they differ by a principal divisor. Notice in particular, I just told you that there is a well-defined notion of a degree of a line bundle on the Riemann surface. That's part of this statement, right? What is the degree of a line bundle on the Riemann surface? You just take any meromorphic section, you compute its degree. And this mumbling here says this is well-defined. Okay? So fix now a line bundle. Fix S, which is a meromorphic section, L. I would like to somehow understand what are holomorphic sections of this line bundle. How can I interpret this space? What's the space of sections of a line bundle? Thank you very much, right? But this, of course, S1, which S1, I guess, in my notation before, which are holomorphic, right? Which is the same as to say F is a meromorphic function on P1 such that f times s, this is my S1, is holomorphic. This is the same as f meromorphic functions, such that the divisor of f times s is non-negative, which is to say, by definition, this is equal to a sum AP times P with all AP non-negative, right? I did nothing whatsoever, right? This is, of course, also the same as all functions f, but a function f on the Riemann surface is determined by its divisor. If I know where the function has zeros and poles, and another function has the same zeros and poles, you divide one by the other, you get the same function up to a constant. I'm a little sloppy about multiplication by constants here, so let me pretend that doesn't happen. And what I will write is correct, just you have to say the words carefully. So this is the same as to say these are, alpha, which are principal divisors on C, such that alpha plus the divisor of S is non-negative, right? I'm just massaging this, right? This is divisor of S plus the divisor of F. The divisor of F is alpha, right? This is a set of F such that F vanishes at all poles of S and may have poles, excuse me, at zeros of S, which you should perceive as a statement with multiplicity. So what does this statement say? It says that this thing should only have zeros, should have no poles. So whenever S has a pole of order 5, F must have a zero of order at least 5. On the other hand, if S has a zero of order 10, F is allowed to have a pole of order up to 10. Okay? That is just language. Okay? So this allows me to think about divisors and in this way, and this allows me to think about sections of line bundles in this way. So sections of a line bundle in the Riemann surface, once I've chosen the meromorphic, there are meromorphic functions in all Riemann surfaces, there are meromorphic sections of all line bundles. Take a line bundle, take your favorite horrible meromorphic section, will have a gazillion poles, a gazillion zeros, it will still have a divisor. Then all holomorphic sections of this line bundle, there might be a none, I don't know, all holomorphic sections of this line bundle are the same as just meromorphic functions on the Riemann surface with bounded pole orders and some zeros required and stuff like that. Okay? So this allows you, in fact, which I don't want to state here, this gives you some isomorphism between isomorphism classes, a set of isomorphism classes of line bundles and isomorphism classes of divisors. So, which is to say, the degree D line bundles on the Riemann surface are precisely parametrized up to isomorphism by points in the degree D Jacobian of a Riemann surface. Okay. Judging by the previous show of hands, I guess that my definition of the Jacobian may not be the definition of a Jacobian of a Riemann surface that is most familiar to people in this audience, right? And that is a well-established fact that this is still the same. Fact, the Jacobian is isomorphic to the usual definition of the Jacobian. I'll write it the way algebraic geometrists like to write it. I think this is how I'd write it. Okay. This is the baby version of the non-motivic version of what Francis was doing. Okay, so you're not allowed to complain now. But it just means you consider the space of all holomorphic one forms which is G-dimensional on a genus G Riemann surface, and the quotient by the lattice dual to the cycles, right? The period matrix is written right here. If you want to get a G by G period matrix as opposed to G by 2G period matrix, you choose a basis here dual to the first G elements here and stuff like that, right? Okay. Huh? Sorry, I mean, yes. So I use C and X for curves in different talks and different papers, depending on the culture. Yes, so there is no X on this talk. Yes. Thank you. This is horrible, right? I don't know which D to put. So all degree D Jacobians are isomorphic to each other. So remark, for any D1, D2, Jacobian D of C is isomorphic to a Jacobian of degree D2 of C, non-canonically. Non-canonical in the sense you just choose any divisor D you like, which is a divisor of degree D1 minus D2, okay, on C, right? And if you take, a divisor, I'm running out of letters, E here, you just send it to, maybe D2 minus D1 is the way I'm doing this. You just send it to E plus D, right? You just fix a divisor of degree, which is the difference of these two degrees, and you just add that to all divisors of degree D1. You'll get divisors of degree D2. Claim this is an isomorphism, because I can tell you what the inverse map is. The inverse map is subtract the divisor. That's somehow boring. There is something hidden here because I'm saying this preserves the principal divisors, but principal divisors know nothing about all of that, so it doesn't matter, okay? So they're all isomorphic. So I am allowed to write this for any D, okay? But you probably know that the Jacobian is an abelian variety. I'm not putting the degree here, right? True, not true. It is an abelian variety, but what does an abelian variety mean? I need to tell you what a zero is. What's a zero? So it has, however, the degree zero Jacobian has a natural zero origin, which is the zero divisor, right? The zero divisor is a well-defined thing. It's just a combination of nothingness. It's zero. There are no points, right? That's a well-defined choice of zero. So that lies in degree zero Jacobian because it's degree zero divisor. Okay? And I don't have such a choice in other degrees so particularly easily. How about polarization? So what does a polarization mean? Remember, this was a line bundle. A line bundle has a zero section, so I have to define for you a codimension one subvariety of this. If you believe this, this means the dimension, the complex dimension is G, right? So I'm supposed to define for you a G minus one dimensional subset of a Jacobian to tell you a polarization. So this can be done. The Jacobian in degree G minus one of C has a natural polarization. Fact, and theta be the locus of divisors D in the Jacobian of C, such that D is equivalent modulo principal divisors to a linear combination of P1 plus PG minus 1. Right? So inside here, so this is the same as to say this is D greater than 0. D is a divisor 1. Okay. So what I just wrote here is manifestly a G minus 1 dimensional set, right? I'll take a linear combination of G minus 1 points in C. This is G-1 dimensional, hopefully, because I can just vary each of the G-1 points. I have to convince you that I will not overcount, which is true. So that's a natural divisor. This is naturally a divisor with degree G-1. Okay? Claim is that the image of this on the principal divisor equivalence is still G-1 dimensional, but it naturally sits here. So what this means is that the Jacobian of degree G-1 has a natural polarization. The Jacobian of degree 0 has a natural origin. This guy also has an involution. Which takes a divisor D and sends it to minus the divisor D. You just flip the signs of all coefficients. If you flip the signs of all coefficients, the degree went to minus the degree, which is still 0. Does this guy have a natural involution? It turns out yes. So natural involution on the Jacobian degree G-1 of C. So I want to take a divisor, that is, its degree is G-1, and I want to send it naturally to some other divisor, which also has degree G-1. And it better be an involution. So morally, I want to write minus D. I have trouble writing, I have no trouble writing minus D, but this is not going to be an involution here, because the degree of this guy is now minus G-1. So I have to compensate. So I have to identify this by identifying Jacobian minus G-1 with Jacobian G-1. So what I do is there is a canonical class. Canonical class. So this is just the divisor of a holomorphic one-form. Any holomorphic one-form on C, because the holomorphic one-forms on C form a line bundle. So the divisors of any two will differ by a function, by a meromorphic function. This is a miraculous thing, right? I have benefited from the fact that the degree of the canonical class is 2G minus 2. The number of zeros of holomorphic one-form is 2G minus 2. Okay? Yeah, this was the most technical part of the interlude. So this is to say that when people say the Jacobian, you should nod, but in the back of your mind, you should keep that you have no idea what they just said. Could be the Jacobian degree 0, Jacobian degree D, Jacobian degree -1, who knows, right? So the correct notion of a Jacobian, which I won't write down, which is well defined, is the Jacobian is a Jac 0 of C, which is an abelian variety, has a 0, has an involution, which acts on the Jacobian G-1 of C, which does not have a 0, does have an involution, compatible with that involution in the obvious way under the action, and which has a principal polarization. Okay? Oftentimes, you will want to identify the Jacobian as degree 0 of C with a Jacobian in degree G-1 of C. That would be very useful. So to do that, you just pick a degree G-1 divisor. But what you do is you use D such that D plus D is the canonical, right? Because that's the natural choice. If you want to identify them in such a way that the involutions are the same involution, you have to do that. And then this is a choice of a spin structure. So a choice of a spin structure, also known as Riemann's constant. This is what identifies degree 0 and degree G-1 Jacobians. There is no such natural choice globally. If you've chosen the basis of A cycles, B cycles, anything like that, yes, you can make a choice. But there is no global way to do this. Okay? Okay, at this, I will just say the Jacobian, and you can then think what I really meant when I said that every time. Okay? So this was an excursion, mildly painful, hopefully, longish, into two things. What are divisors on Riemann surfaces, and what are the Jacobian varieties of Riemann surfaces? And the claim that's implicit on the blackboard is that the Jacobian I've defined this way is in fact the Jacobian you know, and is in fact a principally polarized abelian variety. So I have defined the polarization as the theta, and the claim is that this defines the principal polarization. So the dimension of the space of sections of the corresponding bundle is 1, and it's positive. fact, the Jacobian of C together with theta is a principally polarized abelian variety in the sense of the previous lecture, right? That's what it is. That was an algebraic viewpoint on the Jacobian. Okay. I told you what the theta divisor is. There is much more geometry to that. There is a famous theorem, which I won't prove because I don't really use it for what is going to come in a second. This is called Riemann's, and it is due to Riemann. There are stronger versions due to Kempf and others. This is called the Riemann's theta singularity theorem. What is this about? So in general, if I have an abelian variety, the theta divisor is the zero locus of the theta function, and I can ask you what is it like, what is its geometry, and the answer is usually something, we don't know. On Jacobians, we know much more. So the statement is as follows. For any divisor D in the degree G minus 1 Jacobian of C, you want to know whether this divisor lies in the theta, whether the point D, which is a divisor here, a point D is a divisor on the curve C, which is a point on the Jacobian. The theta function is a function on the Jacobian, right? So you can ask, what is the order, multiplicity, of the theta function, of the theta divisor, at a point D? What does this mean? Theta divisor is a codimension one subvariety of a Jacobian. It's given by one function theta. Okay? And you can ask to what order does a function vanish at this point. Okay? The dimension of the space of sections is 1, right? So you can think that the unique section is called theta tau z, right? Oh, sorry, no, it's not. I'm thinking, and I didn't. So a theta is not a function. A theta function is not a function of the Jacobian. It has automorphic properties, as we know, right? But its zero order is well defined. I said that for curve on the curve, but this is a general statement. And the statement is that this is equal to the dimension of the space of sections of D as a line bundle, on C. So there is, I'm cheating something because I haven't spelled this out fully, and I won't. But if you have a line bundle, I have the associated divisor of this bundle, which is a divisor of any meromorphic section of this line bundle, right? So given a line bundle, I take a meromorphic section. This meromorphic section has a divisor class. If I take any other meromorphic section that got multiplied by a meromorphic function, so the point in the Jacobian didn't change. I'm now saying this goes back and forth. So given any divisor, I can perceive this as a line bundle on a curve. Just by saying the sections of the corresponding line bundle will be the things that have poles and zeros along this divisor, but you can construct a line bundle by hand. I don't want to discuss how this works. Notice this is a very easy to write, but extremely confusing at the first glance something. This is a statement on a curve. So I have a curve. On a curve, I have a line bundle. I have a bunch of holomorphic sections of this line bundle on a curve. That's something on a curve. The curve is just a curve. This is something on the Jacobian, right? So D is a point on a Jacobian. A line bundle on a curve gives me a point on its Jacobian. The Jacobian is a principally polarized abelian variety. It has a codimension one subvariety, the zero locus of the theta function. I'm measuring the vanishing order of the theta function at a point on the Jacobian corresponding to a line bundle on a curve. So what this theorem does, it relates the geometry of the curve and the geometry of theta divisor of its Jacobian. Okay? To get a sense of the simplest case, I told you that the theta divisor was the locus of points where d can be written as a sum of g minus 1 points, right? These things manifestly have a section, because if d is a sum of a bunch of points, then function 1 gives me a section of the corresponding line bundle, right? Remember, hopefully it's written here. So if d is equivalent, means modular principal divisors, which I'm ignoring, to p1 plus dot 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 plus pg minus 1, then 1, right, gives me a section of the corresponding line bundle, right? Because 1, this is a meromorphic function f to p1. The divisor of 1 is nothingness, right? It's 0. So the divisor of 1 times d plus d is d, which has all coefficients non-negative, right? This is a tautology. Somehow all I'm saying is that in this interpretation here, imagine that I started with a divisor d, which was already non-negative, right? All coefficients were non-negative. Then if I just take nothing here, this is satisfied. So the function 1, I can interpret as a holomorphic section of the corresponding line bundle. Okay. Remember our original question that maybe you haven't yet fully forgotten. So the question was how to construct all functions on a Riemann surface with given zeros and poles, all meromorphic functions. But how do we do that? So question, how do we figure out what the zeros and poles are? So suppose for P in C, what are the zeros of theta of? And now I have to think what I'm going to write here. I want to write theta of P, right? That's what I want to write. But I have no idea what I just wrote. Because what is theta? Theta is a function section of a line bundle on the degree g minus 1 Jacobian, right? So I know this as a function of a divisor which has degree g minus 1. If I write a point P, that's not a divisor of degree g minus 1. So this thing here just makes no sense whatsoever in any way, shape, or form, because I need to write theta of, it makes sense, need to write theta of some divisor of degree g minus 1. And since I want to understand how it works, this divisor better depend on P. Okay? That would have a well-defined zero. How can I, starting from a point P, construct a degree g minus 1 divisor? There is a silly way to do this. I mean, maybe not so silly, very interesting. I just take P times g minus 1. That's a horrible idea. The reason it's horrible comes from thinking about abelian variety. So this is multiplication by g minus 1 on the abelian variety. It's a very high degree isogeny. That tells you you'll mess yourself up. Don't do that. No. Okay? So the correct thing to do here is you pick a divisor d. It's convenient to do this in Jacobian degree g of c. And you look at theta of d minus p. Okay? So this is, there is some symmetry. I could switch signs. It's convenient to do it this way. Okay? So if I take a degree g divisor and I subtract the point p, that's a degree g minus 1 divisor. This is fixed. So this is fixed divisor d, and just look at that. Okay? Why would you do that? Because that's the simplest thing you can do. Great question. This is what we're going to look at now. So this is a great choice because I haven't done anything to p. I just put p in there. Maybe, the sign shouldn't bother you too much. But I have done something. I have chosen d. And this will, of course, change what this function looks like. And if I choose a different d, maybe different things will happen, right? And in general, it's very hard to tell what's going to happen, but I want to choose some particular kind of d first, and then I'll tell you this was not a particular kind of d. This was a general kind of d, in fact. But that I won't be able to prove. Okay. So let d, this thing means modular principal dividers, right? Modular principal dividers. So this means as a point in the Jacobian. So this means equality in the Jacobian. So let this be P1 plus PG, where P1, PG are points in C, and let me choose all of them distinct, not to worry too much, okay? That's a possible choice of a degree G divisor. Okay? If you believe that everything is generic and so on, what is the dimension of the space of such choices? The dimension is G, right? Because I can choose each point on the curve independently. So there is a G-dimensional space of choices. The Jacobian has dimension G. So if everything is generic and beautiful and wonderful, these are all points of the Jacobian. This is true. So every point in Jacobian, so this is modular, so this is in IE, in Jacobian degree G, all points can be written that way, but I don't want to go there. Let's just choose such a point, okay? And then I can ask, when is theta of P1 plus PG minus P 0 as a function of P? Right? That's the question here. So observe that if P is equal to Pi for any I from 1 to G, then this thing here is theta of P1 plus dot 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 plus I throw out the Pi plus dot 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 plus PG, right? So this is theta at the sum of G minus 1 points of C, right? Because I just threw out one of the points. What was my definition of theta, which is somewhere up on the blackboard there? It's a divisors of degree G minus 1, which are sums of G minus 1 points. So this is 0. Okay? So I have found that this function theta has at least G zeros at points P1, Pg. If the points Pi collide, it will have zeros with higher multiplicity. Exercise. For this, you need to compute some degree of some line bundle. These are all the zeros. In the language we have developed today, this says a divisor theta of P1 plus Pg minus P, or P1 Pg fixed, is equal to P1 plus P2 plus Pg. There are no other zeros. Okay? So this is good news. This means that given any G tuple of points on the Riemann surface, I have now constructed for you, well, not quite a function, a section of a line bundle, but I'll be forgiven, which has precisely those zeros, right? Okay. So suppose F from a Riemann surface to P1 has zeros at Z1 through Zk, maybe with repetitions, and poles at, let me call them Y, not to get confused with this, at Y1, Yk, which are points on C. Okay? Corollary is, from this discussion is that F is equal to F of P, of a point P, is equal to a constant number times the product for I goes from 1 to k of theta d minus zi theta d minus pi for any, I have to confess, generic. There was some lie up above. Sometimes what could happen is this function could just vanish identically. Okay. So I've written a formula as promised for any meromorphic function on any Riemann surface with prescribed zeros and prescribed poles. I'm sorry. Thank you. Thank you, Simon. Yeah. There is some minor problem with that. I had to make a choice of D, right? And there are many choices. And I'm saying you can make any choice. And your life will be good. Sorry, I wrote the wrong formula. No. Sorry. Forget this. Ignore me for a second. The formula will be correct once I correct it. The shape is correct. What do you want? Sorry. So you take a divisor of degree d, put it here. Divisor of degree d, put it here. Then you put minus p here and minus p here. So this guy will vanish whenever I hit one of these points, right? This will vanish. Even more honest, though it doesn't make a difference. Any. Let me write this honestly so that you maybe regain some trust in me. Maybe not, but the formula will be correct. I rushed too much. The message is that basically, since I know where the zeros are, I can arrange for the zeros to be where I want them to be. The problem is I have g zeros, and I really wanted to get just 1 0. So the other g minus 1 zeros I need to cancel. And that's what I need to do here. Okay, sorry. Okay, now, since this is going to be correct, this will be a theorem. Okay, for any P1, PG minus 1 in the curve C, generic enough, general enough, F is going to be equal to F of P. It's going to be a constant times the product for I goes from 1 to k, theta divided by theta, and it's going to be minus p because I want to match where I want it to vanish. In the numerator, I want the guy to vanish at zi. Here I want it to vanish at yi, so I write that. And here I write p1 plus dot 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 plus pg minus 1. And here I write p1 plus dot 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 plus pg minus 1 plus that. Now this is good. So what's the point of this? So when does the numerator vanish? When does one fact and the numerator vanishes? It vanishes when I get p to be equal to one of these g points. So it will vanish when p hits one of the pi's, or when p hits zi. But the corresponding factor in the denominator will also vanish if p hits one of these guys with the same multiplicity 1. So this will cancel, this will not produce poles. But this will also vanish if p hits yi, that's my pole. Okay, mission accomplished. Oh yeah, I mean, this constant depends on everything under the sun, right? So when this is constant, it's constant in P, right? It's independent of P, that's all. Okay. You can figure out what it is. You can write a formula explicitly for what it is by just evaluating at some point. But there is a huge amount of ambiguity here because I wrote this formula for arbitrary P1 through PG minus 1. I chose mine, you chose yours. You'll get very different formulas. The function better be the same, right? So this constant will depend in a very complicated way on this whole thing. Okay? But I'll get an explicit formula. Okay, any questions on this before we proceed to the second half of the talk? I'm aware that I have 20 minutes. Okay, So now, notice what happened. We had the theory of abelian varieties. Now we had the theory of Jacobians of curves. Not every abelian variety is a Jacobian of a curve. Deciding which ones is a so-called Schottky problem. Okay? What I want to prove for you in the next few minutes, this is a theorem called Andre Weil reducibility. It says the following. Take any curve C, take any points P, Q, R, S in C. Okay. Take this theta divisor. This is theta divisor inside the degree G minus 1 Jacobian. People usually write peak G minus 1. I didn't want to say the word picar, but anyway. Okay. Take the same theta divisor and translate it by P minus Q. P minus Q is the degree 0 thing. So I can just add it to any degree G minus 1 thing, I'm still there. Intersect these two things. Okay, so that's the divisor, codimension 1. Another divisor, hopefully not the same, right? I mean, if it's the same, I don't want to do it. So maybe I should say the points are distinct. I don't want to worry about that. So I've intersected two codimension 1 things and a G-dimensional thing. I should be getting a G minus 2 dimensional thing. I will. For any smooth curve C, this is true. Okay? This is dimension G minus 2. What can I say about it? If I start from a general abelian variety, you can say precisely nothing. Okay? What you can say here is this is contained in the intersection, excuse me, I want to match my notation, otherwise I'll suffer when I'm writing the proof quickly. P minus, it doesn't matter what I write. Let me put parentheses for better readability. So this also translates by this and this point. This is visually must be completely false. Couldn't possibly be true. I mean, it's true, but visually there is something horribly wrong about this. Let's look at the left side. There is a theta divisor. Yep. Translate by P minus Q. Very good. So the left side depends on the curve, P and Q. On the right side, I had R and S, which don't even show up on the left. So I can vary the S without changing anything under the sun. This will vary in the one-parameter family of translates of the theta divisor. And I'm telling you that no matter how you vary this in the one-parameter family, and no matter how you vary this in the one-parameter family, the union of these things will still contain that intersection. Looks manifestly wrong, okay? Or at least manifestly surprising. It is true. It's a very surprising statement. I am unaware of how Weil came up with that idea. Okay? Proof. So my goal is now to prove this, and I probably will run out of time before I am able to explain to you that this is equivalent to phase trisecant identity. So the easy part of this equivalence is that phase trisecant identity implies that going down uses some Kozul cohomology that I cannot possibly develop. So I want to prove this statement because this really can be proved very, very quickly using all of our pain and suffering that we have. Notice that this thing here is a very strong property of Jacobians. In fact, the existence of this trisecants characterizes Jacobians, which I certainly cannot tell you about, among all principally polarized abelian varieties, which is a very hard theorem, which was a conjecture open for many, many years. So this is a highly non-trivial observation, which is highly specific to Jacobians. And I claim that with luck, in the remaining 14 minutes or so, I'll be able to prove this. Okay? Ready for the proof? Okay. So suppose my divisor D lies on the left-hand side, right? And theta intersect theta P minus Q. Okay? So what this means, this means H naught, so H naught is the dimension of the space of sections. I have to start writing this, otherwise it's unreadable. So this means the dimension of the space of sections on C of D is at least 1. And the dimension of the space of sections of D plus P minus Q is at least 1. I may be making a sign mistake throughout, but this is whatever convention I'm using for translate by P minus Q. This is by definition what divisors lie here. These are the divisors that have a section on the curve. That's Riemann theta singularity theorem. I'm not really using Riemann theta singularity theorem. I will never deal with higher multiplicity. I just know that there is a section. Same here. Okay. So I want to know that either C of D plus P minus R or that's what I need to prove, right? Because the first statement is I lie here, the second statement is that I lie here. Yeah? How could I possibly see that? I now want to think about all of this as functions on the Riemann surface. Okay? So I have this. So what does this mean? So suppose, so case 1 is suppose H naught of CD is 1. Okay? So there is only one section, is given by meromorphic function f Cp1 such that the divisor of f plus d is non-negative, right? So the poles are bounded below by the poles I find in D. Okay? Then the divisor of f plus d plus p is also greater than or equal to 0, right? So this, of course, means that H naught of C d plus p is greater than or equal to 1. I'm worried whether I should have done the easier case first. Let me take a look for a second. Okay, no, that's okay. If H naught of C d plus p is 1, then this is also given by oops. Notice that in my convention, then I claim that H naught of C d plus p, I mean, this is contained in here, in general, right? Because these are just functions which are allowed to have an extra pole. Of course, if I'm allowed to have an extra pole, I have it here. If this is 1, then since this H naught is also 1, it follows that f, the divisor of f plus d is greater than or equal to 0. The divisor of f plus d plus p minus q is greater than or equal to 0. The divisor of f plus d plus p is greater than or equal to 0. This is a whole bunch of stuff written, which implies that the divisor of f plus d minus q is greater than or equal to 0. What really happened here? This is a complete triviality written formally. So f is a function on the Riemann surface, which has poles wherever allowed by d. If I take, so in particular, it does not have a pole at p, even though here it is allowed to have a pole at p. But on the other hand, since I know that I have a section here, if the dimension of the space of sections here is 1, then it must be equal to the same as this, because I assumed that the dimension of the space of sections is 1. But then it means that f actually happens to vanish at q, right? But then this means that the divisor of f plus d plus whatever other point was there, s, minus q is greater than or equal to 0, which is equivalent to saying that f gives a section of d plus s minus q, which is equivalent to saying that d lies on the translate s minus q. This was a little tap dance, which is completely trivial. Let me go over it again because it is completely trivial. So what are we doing? I say, suppose I have a divisor d, which lies on the divisor d on the curve C, which has degree g minus 1, which lies on this and this. Okay? This divisor d is a divisor. The sections I interpret as meromorphic functions that I allow to have that have to vanish at the poles of d. I allow to have poles at the zeros of d. Right? Suppose that the dimension of the space of sections of d is precisely 1. Okay? Then it means I have a unique function f up to scaling by a constant, so that its divisor plus d is non-negative. If, in addition, the h naught of c d plus p is still 1, this space contains both this space and the space h naught of d, because I'm just allowing an extra 0. So then all of these three spaces, they're all one-dimensional, and one of them contains the other two. They must be the same space. Then they're given by the function f. But then in particular, the function f gives me a section of d. That's what this means. It gives me a section of d plus p minus q, and gives me a section of, except you probably cannot read, but this was point p, right? But what this means is that in particular from here, I know that f doesn't have a pole at p, while from here I know that f has a 0 at q. So it means at the end of the day, this is to say that the dimension of the space of sections on the curve C of d minus q is non-zero, right? That's what this means. But then, of course, if I add a point S, which allows an extra pole I couldn't care less about, this is still good, right? Okay, so now let's finish the proof. I have required, 5 minutes for that. Maybe I don't have it because this leaks too badly. Well, too late. So what is required to finish the proof is to deal with other cases. So the case was this case. This was one assumption, and this was the other assumption, right? So I have to deal with both of them not being satisfied. Okay. So what we did before was h naught of cd was equal to 1 was equal to h naught of c d plus p minus q. And this we handled, right? Okay, now let me do h naught of cd is still equal to 1, but is less, strictly less than this. Okay? Then there exist two different functions, f1, f2, such that the divisor of fi plus d plus p minus q is positive, right? That's what it means that I have at least two sections. Okay? But then there exist complex numbers alpha, lambda 1, lambda 2, complex numbers, such that if I take lambda 1 f1 plus lambda 2 f2, and I'll evaluate it at my remaining point, which you have forgotten, of course, but I'm trying to prove that theta, in fact, theta p minus q is contained in theta s minus q union theta p minus r. So this point was called r. I can just take a linear combination of these two functions, which will vanish at a point r, right? You could, yeah? This is what happens when you try to do a proof. You don't want to run out of time. Okay, so if this was equal to 1 and this was equal to 1 also, and then this was also equal to then this, and we got something. But here, suppose I have an extra section here, right? Then I have two sections, and I can choose the linear combination that will vanish at R, right? But what this means is that, of course, the divisor of this linear combination, it will still have whatever poles this guy had, but it will now vanish at R, because I just decided that it will. So this means this is greater than or equal to 0, right? This linear combination vanishes at R, which is all I needed. So which, of course, is equivalent to saying that H, which implies that H naught of D plus P minus R is at least 1, which is equivalent to saying that D lies on theta. Okay. So finally, if H naught CD is at least 2, I play exactly the same trick. Then there exists F1, F2, that is the divisor of Fi plus D is greater than or equal to 0. And my life is very nice. So there exist lambda 1, lambda 2 complex numbers, such that lambda 1 F1 plus lambda 2 F2 R still vanishes, right? So then this means that lambda 1 F1 plus lambda 2 F2 gives me a section of D minus R. But this is, of course, a subset of D plus P minus R, because I didn't even need the pole at P. Okay? Which implies that H naught R is at least 1, which is equivalent to say D lies. Okay. That's the end of the proof. So the proof proceeded by just exploiting the language. So I am trying to understand what it means for a divisor D to lie on a theta divisor. It means that there exists a function f, meromorphic function, such that the divisor of f plus d is positive. What does it mean for D to lie here? It means that there exists a function prime or g, whatever, I don't want to call it g, f prime, such that the divisor of f prime plus p minus q is positive. But these spaces are not so far from each other, right? They're both contained in the space of functions such that the divisor of f plus d plus p is positive. And the codimension of each of them in that space is at most 1. And this guy also sits in that space. And this guy also includes this space. So if you write this diagram of spaces, you get a bunch of spaces which each differ by at most 1 in dimension. You just try to see what the possibilities are. These are the possibilities. And you're done. Okay? I am 30 seconds over time, so let me be 1 minute 30 seconds over time, and let me say how you get from here to the trisecant, which I can say in one word. I won't explain why it actually works, but I want to say why is that a relation for theta functions, even though it maybe does not look like that. So what is this saying? So what Weyl reducibility says analytically, it says that if I take any point z, I'll write z to emphasize we're now talking about points on the Jacobian, g minus 1, but I don't care. It says that if theta of z is 0 and theta of z plus p minus q is 0, then this implies that theta of z plus p minus r, theta of z plus s minus q is 0. Right? That's what this means. I mean, lying on the theta divisor means that theta at that point is 0, right? How could something like that hold? Well, it could be that this thing is just a linear combination of these two, right? If this is a linear combination of the two things on the other side, A of z, theta of z, plus B of z, theta of z plus P minus Q. If this were true, this would certainly imply that, right? Because then if this vanishes and this vanishes, this must vanish, right? But let's look at this. These are sections of the theta bundle shifted somehow. So this is equivalent to saying that there are constants lambda 1, so that if I put z plus p plus s minus r minus q, theta of z, plus lambda 2, theta of z plus s minus r, theta of z plus p minus q, is equal to the same expression here. This is just a triviality. This has an automorphic property, so this better have the same automorphic property. Okay? So this is easy. The inverse here is hard. This is Kazul cohomology. Okay, but if I look at that, that's a section of 2 theta as a function of z with some shift. That's a section of 2 theta as a function of z with the same shift altogether, and so is that, right? But we have this formula, which was on the blackboard at the beginning of this time, which expresses something like that as a linear combination of second-order theta functions. Write this down. The second-order theta functions are a basis for a space of sections of something, so they are linearly independent. So you must have a linear dependence. That's phase trisecant identity. End of proof. This direction is technology. Not so hard, but far outside what we've talked about. Thank you.